Right, today we're going to look at factoring polynomials. So to start with, we need to look at factoring monomials, right? So what we need to do is we need to break down each term into its essentially as prime factors, right? So we look at the coefficient, and we break that down to its prime factors, and then we list all of the factors of the variables, right? So for 8x to the fifth power, for example, right, we're looking at, well, do a prime factor tree for your 8. That's going to be 2 times 4, and 2 times 2 is, so your prime factorization of 8 is 2 times 2 times 2 for 8, right? And then your factorization of x to the fifth power is, well, 5 x's, right? X times x times x times x times x, right? So this is your complete factorization of 8x to the fifth power. Now I know it says, what are all the factorizations of 8x to the fifth power? That's a pretty big ask, right? There's a lot of different combinations there, right? And yeah, trivia question, if you remember from our previous unit on probability, right? You go to your combinations and you figure out how many different combinations do you have here. Recognizing, for example, that another way of writing this, you've got to include the 4 as well. You can actually write this as 2 times 4 times x times x times x. And you know what? I'm going to put a times x squared in there for the last one, for the last two, just so that you see that the number of x's is still 5. X squared times x times x times x is still x to the fifth, right? So this second one here is a factorization of our monomial 8x to the fifth power, right? And of course, I mean, you could also say, well, 8 times x, let's say x cubed times x squared. That's a factorization also, right? It's just not a very useful factorization, right? So the factorization that we're most interested in is this one, is this one right here. Okay, that's the factorization that we're most interested in, because that's the factorization that can help us do other stuff like getting the greatest common factor and pulling out common factors out of polynomial expressions. Okay, so let's take a look at another one. All right, the factorizations of 18x cubed. Once again, we're going to take our prime factorization of 18 is 2 times 9 and 3 times 3. So 2 times 3 times 3 is our prime factorization of 18. And then we tack on x times x times x along with it. Those are our 3 x's from x cubed, right? So that's our complete factorization, right, of 18x cubed. Once again, we could look at this in various different ways. We could say, well, this is the same as saying, let's say 6 times 3, that's 18 as well, times x squared times x, if you wanted to. That's a factorization. Not a very useful one, but it is a factorization, right? And we could look at another example, say 9 times 2 times x cubed. That is a factorization, not a very useful one, but it's a factorization. Okay. Once again, the only one that we're really all that interested in is the complete factorization. That's the one that we're actually interested in. Now, the reason for that is that this is the one that can actually help us solve greatest common factors. So if we kind of look back at greatest common factors, a quick review of greatest common factors, if we were to find the greatest common factor of 18 and 8, right? So these two are 8 and 18, it doesn't matter which, right? Same difference, right? We've got 8 here and 18, right? So we look at, well, what do they have in common? We've got a 2 that they have in common and nothing else, right? So that's all they have in common. So the greatest common factor of 18 and 8 is 2, right? So likewise, we can actually look through our complete factorization to find out what is the greatest common factor of 8x to the 5th power, right, and 18x to the 3rd power. What is the greatest common factor of those two, right? So we know first of all that we've got a 2 in common, right? That's the first term. We've got a 2 in common. That's the coefficients dealt with. And then we have 3 x's in common. So we know that each of them has at least 3 x's. So we've got x cubed, right? So our greatest common factor of 8x to the 5th power and 18x to the 3rd power is 2x cubed. And let's see what that means for each one. So 8x to the 5th power, that means 8x to the 5th power can be written as 2x cubed times 4x squared, right? Because 2 times 4 is 8, and x to the 3rd times x squared is x to the 5th, right? Likewise, 18x cubed can be written as 2x squared times 9, right? So what we could have said here is like the useful factor out of the useful factorization of each of these is actually 2x cubed, right? Times whatever the rest is. So times 4 times x, and in this case, this last one right here, 2x cubed times 9. Those are the two factorizations that are actually in any way useful, at least in this context, right? Okay? So we're going to bring that idea straight into greatest common factor and apply it to each of these two examples going forward. So these two examples going forward, let's look at what we've got. We've got 12x squared. Well, that's equal to, our prime factorization of 12 is, it's 2 times 6 and 2 times 3, just to show you there, right? So we get 2 times 2 times 2 times 3 times x. And for 18x, we have 2 times, we already have it up here, 2 times 3 times 3 times x. So if we combine those two together to find the greatest common factor, we see we've got a 2 in common, we have a 3 in common, and we have an x in common. So that's equal to 6x. That's our greatest common factor. Okay. Likewise, we're going to look at 10x cubed. That's equal to 2 times 5 times x times x times x. And 4xy is equal to 2 times 2 times x times y. Right? Bring it all together, and we have 2's in common, and we have an x in common, and that's it, 2x. Right? So the greatest common factor of 10x cubed and 4xy is equal to 2x. So far, so good. All right, we're going to start applying this into polynomials now. Right? So let's take a look at applying this into polynomials, factoring some polynomials. Okay, so the first idea here is, and just a word of warning, if you've got your printout here, there's actually a typo right here. Right? There's a typo right there on your printout that says AB plus BC. So just take a moment to change that if you've got the printout. Right. So the idea here is what we can do um, we know our distribution, right? So A can be multiplied into these parentheses, and you get AB plus AC, right? So A times B and A times C is AB plus AC. Likewise, it works both ways, right? You can also factor out the A to get A times B plus C, right? So it works both ways, right? So to illustrate that, let's take a look at these first two examples, right? So notice that right here, this 3x squared, we can distribute that in here, right? And we get 3 times 4 is 12. X squared times x is x cubed, right? 3 times 3 is 9. And x squared, well, just 9, x squared, right? So our factor that we can factor out the 3x squared, and if you really want to check this, and we will real quickly, we can do our factors. This gives us on the left-hand side, this gives us just to show that 3x squared is actually the factor that we can pull out, and there's nothing else. We have 2 times 2 times 3 times x times x times x plus 3 times 3 times x times x. As you can see right there, the 3 on both sides and 2 of the x's on both sides is all that we can factor out of that expression. Okay, the next one here, so we just looked at distributing in. Notice that both of these expressions here have a common factor. The common factor essentially, if we look here at our AB plus AC, this is the same. This is equivalent to saying AB plus AC, right? Notice the 2AX is your A, right? Which means that we can factor out the 2x out of this expression, and we can say that this is 2x times what's left, 3x plus 5. Right? So we can factor out the 2x as well, just the same way as we did. So it works both ways. It works like you can distribute in any expression into parentheses, and you can factor out any common factor out of the parentheses. Right? So it works both ways. Okay, a few ways to kind of look at this in terms of polynomials, because there's a few things you got to watch out for. And grouping is a key component of this. So let's look at this first example right here, or well, third example, I suppose. All right, this example right here, we note, if we look carefully, we note here that we have well, first of all, this polynomial has no parentheses. It's all just addition and subtraction, which means that we could rearrange this in any order that we want, right? So if you see patterns like jumbled up within the polynomial, you can arrange that part together and group it together to try to factor out a common factor that just that part of the polynomial has. To illustrate that point, see this 3x minus 3? I notice that they have a common factor that is 3. So I'm going to factor out just that 3 out of this part of the polynomial. And I'm going to ignore the rest of the polynomial for now. Right? So 3x minus 3 is the same as saying 3 times x minus 1. All I did was take 3x divided by 3 and negative 3 divided by 3, I get x minus 1. Okay? Now when I'm looking at the left-hand side, what's left, I notice, well, these they've got many common factors, right? X is the common factor ultimately, but as the greatest common factor, they actually have x to the power of 4 as the greatest common factor. So I'm going to factor out the greatest common factor, x to the power of 4. So x to the power of 4, so x to the power of 5 divided by x to the power of 4 is x. Negative x to the power of 4 divided by x to the 4 is negative 1. And now I notice that there's actually something useful that is coming out of all of this, right? Now, just a pause note here for a second. Note that if, for example, factoring out x to the power of 3 was the useful factor to pull out, I don't always have to factor out the greatest common factor. I can factor out any factor I like, right? That makes it useful, right? But in this case, we're factoring out the greatest common factor, and that, in the examples you'll get, are the most common, right? So what I notice here is I factored out x to the power of 4 on this side, and now I notice I have two common factors in each of these terms. I've got two terms, right? I started with 4 terms. Now I have 2 terms, and each of those terms has a common factor itself. X minus 1 is the common factor. So I'm going to factor out the, so here's my common factors right here, and I'm going to factor them out of the expression. Okay, so I get x minus 1 factored out of the expression, and I'm left with x to the 4 plus 3, right? Which is kind of fascinating, right? I just factored out the greatest common factor, and I ended up with two binomial factors, which is fascinating to see, okay? And you'll often end up with that when you've got polynomials, when you're actually dealing with polynomials. Anything greater than a quadratic, you'll typically get some. Well, if you can factor common factors out, you'll get a product of binomials or trinomials. Okay, let's look at these examples right here, because these examples are super fascinating examples, right? And actually, what I'm going to do to avoid writing it twice, I'm going to scroll down, because this relates to what's going on down here. Okay. All right. So this left-hand side here, all right, we can factor this out. We notice that this is the same as saying x squared minus 2 squared. Right? That's just something to note right there. And with that, we recognize that this is a quadratic, right? It is a quadratic that we're familiar with. That it's a quadratic pattern we're familiar with, right? So we can factor it out, okay? So x times x is x squared. Positive 2 times negative 2 is negative 4. And of course, we observed there, of course, if we FOIL this out, we have x squared plus 2x. I should do the minus 2x first. X squared minus 2x, right? And then x minus 2x, and then x times 2 is plus 2x, right? And then I've got minus 4, right? Because 2 times negative 2 is 4. And of course, this center part here cancels out, okay? So what we see here, notice the x plus 2, x minus 2. I'm going to kind of highlight this right here, okay? We see a u plus v, u minus v pattern. We'll talk about that in a minute, okay? So our first factorization is right here. Our second factorization, this again is a quadratic, so let's set up our binomial factors for a quadratic, okay? We're going to have an x, right? Let's look at the signs. Our last term is positive, so the signs must be the same. Our second term is positive, so both signs are positive, right? And we're looking for the factors of 5 that add up to 6. Well, 5 is prime, so it can only be 1 and 5. So, and 1 plus 5 just happens to be 6 as well. So we've got 5 and 1. So 5 plus 1 is 6. 5 times 1 is 5. And here is our complete factorization of our two polynomials up above. Okay. Now, I'm going to point out right at the very beginning that this quadratic right here that we see right here, because there's two separate what I'm going to call v terms, right? These aren't the same, so we can't label them to be the same. We can't say that They're both v, right? Because v can't be both 5 and 1 at the same time. So this is a form of a quadratic that that we cannot use a pattern. We cannot use a pattern for. Okay, so I'm going to leave that aside right away, that you recognize that we can't use a pattern for that form. Okay. Now what we're going to look at is back again to this x squared minus 4 quadratic type. So notice I said this was x squared minus 2 squared, right? Notice both terms are square terms, okay? And this gave us a pattern of x plus 2, x minus 2 when we factored it out. This was because our center, this was because our constant term is negative. So our constant term is negative, and we also observe that this center is gone, okay? So we're not going to have a combined term in the middle because it cancels out. But we're going to have a negative, right? We're going to have a negative in our polynomial, right? And both terms are going to be square terms. So let's take a look at this one here. We've got a 16x squared, which I observe here is the same as like 4 squared x squared. That's a square term, right? And this one here, 49y squared, is 7 squared y squared. That's a square term. Okay, both of those terms are squares. And I observe also that we've got a negative, right? So that tells me a few things. It tells me since both terms are squared and I have a negative in the middle, this here must be a difference of squares. Okay, so this must be a B-type pattern, a U plus V, U minus V pattern, right? The center of it, the combined part, what you would see as maybe an XY part, it doesn't exist, right? And we'll multiply it out later on. We'll FOIL it out later on so you can see it. Okay, so we see that this is a pattern, a U plus V, U minus V pattern. And what we see here is that our U must be this. Well, let's break it out. 4x squared. Sorry, 4 squared x squared is the same as saying 4x all squared, right? This here is 4x, right? Our V is, well, 7 squared y squared. That's the same as saying 7y all squared. So our V is 7y, right? Again, like I said, both sides are squares, okay? This 16x squared is 4x all squared. The 49y squared is 7y all squared. So we've got a U and a V right there. So we can factor this out using our rule here. We can say this is the same as saying 4x plus 7y times 4x minus 7y. And let's verify that that's true. Okay, let's FOIL it out. 4x times 4x, 4 times 4 is 16. X times x is x squared, right? 4x times negative 7y, that's negative 28xy, because x times y, right? Okay. And then 7y times 4x, again, is positive this time, 28xy, right? So we can see right away these cancel out. And then 7y times negative 7y is negative 49y squared. Okay, so we just verified we're back where we started. Pretty useful to be able to take an entire term, right? Take an entire term here, right? And just replace it with a letter, okay? And solve for that letter first, right? Okay? Because if you just have the letters, you're not worrying about, you know, it could be a very complex term, but you can do it, or you can just let it equal to a single variable and then go from there. Okay. The final pattern is this, and they're two separate patterns: a u plus v squared pattern or a u minus v squared pattern. And again, it's quadratics, right? And let's go back to our, what we observe from our quadratics, right? If the last term is positive, right, we know that the signs are the same, right? Okay, we know that the signs are the same, which means we're not dealing with b here, right? So our last term is always going to be positive, okay? If our last term is, if our middle term is positive, we know that we're going to be dealing with a positive in our factor, right? The two factors are both going to be positive, right? They're both going to be sums, right? If our middle term is negative, then the sign in the middle is going to be negative. So for this one here, we notice it's a positive. Our middle term is positive, and therefore it's a u plus v squared pattern. Okay? If this middle term here was negative, it would be a u minus v squared pattern. Okay? Again, we know this is true. First of all, let's kind of back up a little bit, because once again, each side is a square, right? 4x squared is equal to 2x all squared, right? And 81y squared is equal to 9y all squared, right? So we've got u is equal to 2x and v is equal to 9y, right? Now what we should, before we proceed, we should just verify real quick that our center will match, okay? So 2 times 9 is 18, times 2 is 36. Remember that you always get your center terms is always twice. It's either going to be canceling each other out, or it's going to be doubling a positive or doubling a negative, right? So in this case, it's doubling a positive. 9 times 2 is 18, times 2 is 36. So that, and our xy, that's going to work out. So factoring the expression, and we'll verify as well. Factoring the expression, we see we actually have an expression which is 2x plus 9y all squared. And let's verify that's true. So 2x plus 9y times 2x plus 9y, right? And let's FOIL that out. 2x times 2x is 4x squared, right? 2x times 9y is 18xy. 9y times 2x is 18xy. And 9y times 9y is 81y squared. And see that middle there becomes 36xy, right? So we verified that's true. All right, that's it for now. If you have any questions, please feel free to ask or leave them in the comments below.